Okay, hello everyone. It's a great pleasure for me to introduce our second invited speaker, is Maria Chudnovsky. Maria is a professor of mathematics at Princeton University. She's very well known for fundamental contributions in graph theory, including some very important ones that came quite early in her career. I think without a doubt her most famous contribution is the proof of the strong perfect graph theorem together with Robertson, Seymour, and Thomas. It has been the stronger perfect graph conjecture for 40 years, I think, before the proof. I think the paper is 2006, but perhaps the result was around 2002 that was first announced. There are also many other important contributions in her career, including the first polynomial time algorithm for recognizing perfect graphs and a structural characterization of Cloffe graphs. So I'm very happy to welcome you here, and Maria is going to talk about forbidden induced subgraphs and 3 decompositions, and the floor is yours.
Thank you very much. Thank you for having me. It's great to be here. I would have preferred to be there in person, but hopefully next year. So I'm going to talk about work that this is my Corona talk, because basically I started working on this just at the start of the pandemic, and we proved some theorems that I'm very happy about. So I'm going to tell you about them. I've been giving a talk under this title for a long time now, but it's always a different talk because it's very much work in progress. We keep proving things. So please don't be discouraged by the fact that it's the same title. It's just the same kind of general topic. And different work here, different results here is joint work with different people. So I'll mention who did what. All right, so I'm a graph theorist. I work on graphs. Graphs have vertices and edges. All my graphs are simple, so an edge is the same as a pair of vertices. There's nothing complicated. And what I have focused on for most of my career is the structure of graphs defined by forbidden configurations under vertex deletion. So in other words, I tell you, you cannot delete vertices from this graph to get a certain configuration, and then I want to deduce some properties of this graph, or ideally to describe the structure of all such graphs. But this is kind of the context. And this is also called for graphs defined by forbidden induced subgraphs. So let me say this more precisely. An induced subgraph means you're allowed to delete vertices, and then if you delete a vertex, you have to delete all the edges instead with this vertex. But that's all you can do. What you're not allowed to do is to just remove an edge from the graph, right? The most common containment relation between graphs is remove some edges, remove some vertices. So this is not that. Here you're allowed to remove vertices, but you're constrained on how you can get rid of edges. So here it is here it is written down, I should say. So H is an induced subgraph of G. If the vertex set of H is a subset of the vertex set of G, and then 2 vertices are an edge of H. If, well, first of all, they both need to be vertices of H, right? You shouldn't have deleted either of them. And secondly, it's if and only if they were an edge of G. So here's an example. This is G. This, you can see my mouse, right? This is an induced subgraph of that, because to get this from that, you delete this vertex in the middle. This is not an induced subgraph of that, because to get this from that, you would need to delete this edge, and that's not an allowed operation. You're not allowed to just delete edges. And we say family is hereditary if it's closed undertaking induced subgraphs. So what I'm interested in is properties and structure of hereditary families. Now, just one more thing I want to say. So here, right, I said H is an induced subgraph of G. In particular, the vertex set of H is a subset of the vertex set of G. I'm going to abuse this notation and say everything up to isomorphism. So I say I'll say H is an induced subgraph of G to mean H is isomorphic to an induced subgraph of G. Right? And everything here will be about induced subgraphs. So if I say contains, it's an induced subgraph. If I say free, it's an induced subgraph. Everything is an induced subgraph. Probably the most well-known, one of the most well-known hereditary families is the family of perfect graphs. So just remind you what that is. The graph is perfect if the clique number and the chromatic number are the same for all induced subgraphs, including the graph itself. All right, so clique number is the largest number of pairwise adjacent vertices. The chromatic number, probably know what it is. And it's a theorem, the strong perfect graph theorem with Neil Robertson, Paul Sieber, and Roman Thomas. And it says a graph is perfect if and only if it doesn't contain certain induced subgraphs. So what induced subgraphs? Odd cycles of length at least 5 and complements of odd cycles of length at least 5. That one direction is easy. It's easy to see that if a graph is perfect, then it doesn't contain this and it doesn't contain those, because these and those don't have the property that the clique number and the chromatic number are the same, but the other half is hard, the other half is a strong perfect graph theorem, that if you don't contain this and you don't contain those, then you're perfect. But this was conjectured by Claude Berge in the mid-1960s, and then we proved it in 2003 to 2006, depends whether you measure by the time we thought we had the proof or by the time the paper appeared. But anyway, that's been done. And there are all kinds of nice things about this property, or about this family. So, right, so it's a family that's defined by forbidden induced subgraphs. So it's obviously hereditary. It has an interesting property with respect to coloring. It has another interesting property, which is a theorem of Groce, Lowas, and Shriver, that says that you can compute the clique number in polynomial time. And you can strengthen this. You can compute max weight clique. You can compute max weight stable set. You can actually find an optimal coloring. There are all kinds of algorithmic problems that are NP-complete in general, but you can solve them in polynomial time in perfect graphs. But they all follow quite easily from this. So this is a lovely, lovely hereditary family. It's nice for coloring. It's nice for algorithms. Let me just say something about this theorem. So the way Groce, Lowas, and Shriver prove it, they express the problem of finding maximum weight clique as a semi-definite programming semi-definite program, and then they apply methods from combinatorial optimization to solve this problem. So there's a variant of that that's still open, and that is find a combinatorial algorithm. Find an algorithm to compute, let's say, max weight clique in perfect graphs, but without going through combinatorial optimization. So one way to say it, kind of a rule of thumb, is an algorithm that doesn't use division. Another way to say it is an algorithm that you can easily describe in terms of the graph. I mean, you could argue that the run of the ellipsoid method on the semi-definite program, you could describe in terms of the graph, but in fact, nobody can. People tried and we can't. I don't know why it's so hard. I mean, I'm not a combinatorial optimizer, but I'm a graph theorist and I can't do it. I think the other people can't do it either. So, but somehow, say this, find an algorithm like this in terms of graphs. That's a lovely open problem that I'm very interested in, and I'll say something about it later. Okay, but for now, perfect graphs are an exemplary hereditary family. So then one might ask, is this something that's common to all hereditary families? Are they all nice? And the answer is no. They don't all behave nicely with respect to coloring. So one thing you might hope for is that the chromatic number is bounded as a function of the clique number. In perfect graph, it's equality, but I'll even settle for this. I consider this kind of a relationship to be a good thing, but it's false. Like if you look at the family of triangle-free graphs, there is no such F. That triangle-free graphs with arbitrarily large chromatic number, and of course, clique number is 2. It is also not true that all hereditary families have nice algorithmic properties. For example, you can't compute omega in polynomial time, even for graphs with no stable set of size 3. Stable set means set with no edges. So I should say it is NP-complete to compute. I'm not going to make statements about whether you can or cannot do it, but I will tell you that it's NP-complete to compute omega in graphs with no stable set of size 3. So somehow perfect graphs are an exception, not a rule. But there is one nice conjecture, one sort of way one conjectured way in which hereditary graphs are different from general graphs. I'm sorry, in which families of graphs with forbidden induced subgraphs are different from general graphs, and that's the Ereshkigal conjecture. So what the Ereshkigal conjecture says is that for every h there is an epsilon. So let me say it qualitatively now. For every h, if I look at graphs that don't contain h as an induced subgraph, then they have either a surprisingly large clique or a surprisingly large stable set. That clique is omega of g, alpha of g is the size of the largest stable set. So the conjecture is for every h there's an epsilon, so that if h is not an induced subgraph of g, then either the stability number of g or the clique number of g is at least the number of vertices of g to some power. And now why is it surprisingly large? Because if you don't forbid anything, that's log the number of vertices, so it's different. And then this is still open. There's been some progress on that recently, which I'll mention, but this is still open. This is kind of the nicest conjectured statement about all families defined by forbidding one induced subgraph, as far as I know. Okay, so let's move. So if not all hereditary families are nice, then it makes sense to ask which hereditary families are nice, and this is, you know, an infinite field. But I'll focus on two kinds of nice. I'm interested in trying to describe their structure, and I'm interested in trying to answer the question of efficient algorithms. I will not touch on this property here, right? When is the chromatic number bounded as a function of the clique number? There are theorems about that, but I won't talk about that now. So I'm just talking about structure and algorithms. And when you talk about structure and algorithms, the notion of tree decompositions comes to mind, because this is a very well-known structural tool to design efficient algorithms. So I'm going to remind you what the tree decomposition is, and I'm going to say two things. One is, this slide is for a very niche audience. If you don't know what the tree decomposition is, you're not going to learn it from here. If you don't know what the tree decomposition is, then you really don't need this slide. But this is for people who kind of know but forgot. But on the plus side, it's not that important. This is kind of a survey talk of everything. So if you don't exactly remember what the tree decomposition is, it's okay. But let me say it anyway. So I have a graph G, and tree decomposition is a way to represent G by a tree. So I have a tree T, and I have a function X, right? So tree T, and what X does, for every vertex of this tree, it assigns a subset of the vertex set of G, right? So for every V vertex of T, there is X of V, which is some subset, and we call it the bag at V. And then there are two rules. So one rule is every edge is in some bag. Every edge of G needs to be captured in a bag. And the other rule is that if I look at the vertex of G and I look at its support, namely I look at the vertices of the tree in whose bags it appears, then the support is connected. The support is a subtree. So these are all the rules, and let me just do a couple of examples. So first of all, let me do kind of a trivial example. For every graph, here's its tree decomposition. Take a one vertex tree and map all the vertices of G to that vertex. So that's a tree decomposition, right? It satisfies these two properties. No, not an interesting one, but at least every graph has a tree decomposition. So now let's make it a little bit more interesting. So here's a graph. So in this picture, blue is the graph, and pink is the tree that I'm using for the tree decomposition. So here, this is the graph, and I'm going to construct its tree decomposition using the same tree. So what I do is I fix a root, which I call 3, and then for every vertex of this graph, there is a unique path to the root. And so it has a unique neighbor in the path to the root. And I'm going to assign to this vertex a bag which consists of it and its unique neighbor in the path to the root. So for example, 1, here's its path to the root. The unique neighbor of 1 and its path to the root is 2. So I'm going to assign 1, 2 to this vertex. 4, its unique path to the root is 3, 4. Its unique neighbor in this path is 3. So I'm going to assign bag 3, 4. And you can check that every edge is captured and that every vertex has connected support. And notice that here I used bags of size at most 2. Now here, so I won't tell you how I constructed this tree decomposition, but you can check that this is a tree decomposition of that. And I used bags of size 3. And it's significant. So what I'm interested in is to know how small are the bags that I can use. I don't care how huge the tree is, but my goal is to make the tree small. My goal is to make the bags small. And if I can do it with small bags, I say the graph is tree-like, close to being a tree. And if I can't do it, if I need huge bags, then I say the graph is very far from being a tree. So this graph is a tree, and I was able to do it with bags of size 2. This graph is not a tree. I did it with bags of size 3, and in fact, it's a theorem that you couldn't do it with bags of size 2 because it's not a tree. The only graphs that have tree decomposition with bags of size 2 are trees. So now let me say this more formally. So given a decomposition, this width is a maximum of a bag minus 1, and that's designed so that the tree width of a tree is 1. Seems kind of fair. And then the tree width of a graph is the minimum of all decompositions of the width of the decomposition, right? And this is what I already said. If G has small tree width, then it's close to being a tree. Okay, so now why do we care? Well, if you have bounded tree widths, then there's a trick that probably I don't need to tell you about called dynamic programming that you can use to design efficient algorithms on the graph, to design efficient algorithms to compute things such as optimal coloring, maximum weight stable set, right? And again, here's the definition of what a stable set is. It's a set with no edges, some other problems. The key property here, so there are two things. One is if I remove a bag, then it kind of disconnects the tree. I fix a root and I remove a bag, and then the branches hanging off this bag become disconnected from the rest of the tree and from each other. And the second property is, but this is any tree. I didn't say anything about the bags being of bounded size. But the second important property here is that whatever problem you're trying to solve, the optimal solution can only meet the bag in a constant number of ways, just because the bags have constant size. So let's say I'm solving max stable set. So if bags have size 100, then the biggest stable set can meet a bag in at most 2 to the 100 ways, and that's a constant. So there's an interesting direction that I'm thinking about. What can replace bounded tree widths? Right? Can you find a decomposition where somehow you can ensure that an optimal solution to the problem you have in mind meets every bag only in boundedly many ways? And in fact, polynomially many ways is good enough. So this is not really a subject of this talk, but this is a subject I'm working on and thinking about. What is as good as bounded tree decomposition in terms of how complicated can, so it's a tree decomposition where an optimal solution meets every bag in some constrained way. Okay, so this is just kind of some philosophy about tree decomposition, but let's go back to the classical setting, which hereditary families have bounded tree widths. So the results known about that, if instead of hereditary you say minor closed, right? There's a theorem that if you have huge tree widths, then either you have a huge clique minor or a huge grid minor. But what about induced subgraphs, right? What if I don't want to think about minors, I want to think about induced subgraphs. So what can you say then? What do you need to exclude as an induced subgraph to get bounded tree width? So we have some intuition from the world of minors. You have to exclude a big clique, you have to exclude a big complete bipedal graph. When you think about minors, you don't need to list them both because a big bipedal graph has a big clique as a minor, but when you think about induced subgraphs, you do. You need to exclude, so this is a picture of a wall. I'm not going to tell you exactly what it is, but this graph is a wall. You can make it bigger. And then you can subdivide the edges. And that's a subdivided wall. And you can convince yourselves that subdivided walls have big tree widths. So you have to exclude the subdivided wall. Now for minors, this is it, but for induced subgraphs, there are tricks you can do, right? It's harder to contain something as an induced subgraph than as a minor. So if you take the line graph of this, so take a subdivided wall and take its line graph. And what that means is you replace vertices of degree 3 by triangles, right? You do a Y delta operation on vertices of degree 3. Then you get this graph, right? So here, the triangles are not subdivided, but all other edges may be subdivided. And that's another graph with large trivets. So, and this doesn't contain that as an induced subgraph, and that doesn't contain this as an induced subgraph. So you have to include them both, to exclude them both if you're hoping to get something with bounded trivets. So, but this is everything, you know, this is what we get from our knowledge about minors. So, you know, you might hope this is it, but the answer is no. So Cintiari and Tornion have this very sad construction. They constructed graphs with no induced even cycles and no clique of size 4, and with arbitrarily large trivets. So let's just think about it for a minute. I claim if I look at this class, so certainly you don't contain big cliques, you don't contain big complete byte graphs, right? Because you don't even contain C4. C4 is a K22. And it's not very hard to convince yourselves that this and those contain even cycles. The reason is this contains what's called a theta. A theta is 2 vertices with 3 induced paths between them. And this contains what's called a prism. It's 2 triangles with 3 induced paths between them. And every theta contains an induced even cycle, and every prism contains an induced even cycle. And so if I forbid all induced even cycles, then that means I forbade thetas of prisms. That means I forbade walls and their line graphs. So certainly, right, in this class, I forbid everything that I listed on the previous slide, and still the theory is huge. So that's not good news. So that means there are other abstractions. I have to look further. But then Cintiari and Tornion noticed that in their construction, the max degree is huge. The max degree is, let me not say what the max degree is, but the max degree is huge. Right? To get big K, you have to get big, you have to make big max degree. So then they said, what if we bound the max degree? What if I say no induced even cycle and max degree is bounded? Can you then prove, right? So if the max degree is bounded, then there's no big clique and no big complete backlight graph. So that would be, right, that would fall into the general framework of that first slide. So then they asked what's going to happen in this setting, and in this setting, it turns out it is true that the theory is bounded. So it's a theorem with my student Tara Abrishami and with Kristina Vushkovic, who proved it about a year ago, that if you look at graphs with no induced even cycles and no bounded degree, then the theory is bounded by some function of the degree. And I should mention that it's conjectured by this group of authors, and they proved it for delta at most 3. They proved it for max degree at most 3. And they also made the conjecture that if I bound the max degree, then the intuition we get from graph minors is in fact correct. So if you forbid bound the max degree, and I'm going to write it this way here, forbid big cliques and big complete backlight graphs. In fact, I don't even need to say that because the max degree is bounded. So certainly big cliques and big backlight graphs are not allowed. And then you forbid subdivided walls and functions of subdivided walls of some size, and you get bounded trivets. And so most of what you're going to see here was motivated by this conjecture. Right, so you see how this is a special case of that conjecture. And now I'm going to show you all kinds of other theorems that are sort of evidence for this conjecture being true. Now, I should say, I don't know if this conjecture is true because somehow everything was going very well and then we got stuck. And so maybe the conjecture is false. Maybe there's a lot of evidence that it's true, but it's also false. But I don't know. I'm not betting on this conjecture, but I'll tell you what I know. Okay, so I should say we came as far as having an actual construction that was a candidate for a counterexample, but then we found a big wall in it. So that wasn't a great success. All right, so let's keep going. And I'll mention something about the proof of this theorem, because it's a proof technique that we developed that we think is useful for all kinds of things. But let me tell you about some more results first. Okay, so here's another special case of the conjecture. So this is, I call it a halfway step, but it's somebody once said this is a halfway step, but it's a smaller half. So what I'm going to forbid is a long claw. What's a long claw? So a claw is just a K13. And now I take a K13 and I subdivide the three edges, subdivide them many times. And that's a long claw. So STTT is what you get from K13 by subdividing every edge T times. So this is a picture of S333. This is a picture of S111. Right? And so I'm going to forbid a long claw and the line graph of a subdivision of a wall and bound to max degree. And then the term is that the tree width is bounded. Right, so I wanted to, just to remind you, I wanted to forbid this and that. So I forbid this, but here I forbid something. I forbid a long subdivided claw. Okay. And this is a theorem again with Tara Abrisham and Jamil Debek from my students, and with Pavel Chudnovsky, that in this case the tree width is bounded. So you think there's a kind of a symmetric statement if I forbid a wall and instead of a subdivided claw I take a triangle and give it three long legs. But that we can't prove. Even if you forbid a triangle, we still can't prove it. So this is kind of where it is now. No big wall and no triangle, and I'm completely stuck on that case. Okay. So, but let's keep going. So we proved it for this. And now let me tell you something about the proofs, because the proofs kind of use the same machinery and then you plug in different things at the end. So let me talk about the machinery a little bit. And let's say, just for clarity, I'm now focusing on trying to prove this theorem. That if max degree is bounded and you forbid induced even cycles, then the tree width is bounded. Okay. So let me remind you what the separation in a graph is. It's a partition of the vertex set into two subsets, not necessarily disjoint, but right. So it's two subsets X and Y, and there are no edges from X minus Y to Y minus X. Right. The only edges between X and Y are incident with vertices in the intersection. And the order of the separation is the size of the intersection. And there's I call it a theory of separation. We don't actually need to use it, but it just ties it to some historical context. So you say two separations are non-crossing if this happens. So you can exchange X and Y and X prime and Y prime, but for some permutation, you have that X is a subset of Y prime and X prime is a subset of Y. And what that means, if you draw a picture, it means that the separation, you can kind of see that one separation is further to the right of the other. Our intuition of further to the right is what this is. It's not that they break the graph like this, and there are four non-empty bits to the graph, and you can't compare them, right? Okay, and again, I'm not saying this precisely because it's not important right now. But there's a theorem of Robertson and Seymour that connects non-crossing collections of non-crossing separations to 3D compositions. So what they prove is that if you give me a set of non-crossing separations, and there's a 3D composition where the separations that correspond to edges of the tree are precisely the separation in your collection. Right? So if you think about the 3D composition, if you delete an edge, that gives you some separation in the graph, right. So it's a separation, right? Like so you take an edge of the tree and you look at what's on this side of the edge and what's on that side of the edge, and that's a separation in the graph, and that's what I mean by when I say separations that correspond to deleting an edge, and they prove that for every non-crossing collection of separation, there's a 3D composition that in some sense corresponds to it. So if you're interested in finding 3D compositions of a graph, it's a good idea to start with non-crossing collections of separations. Okay, so now the thing about hereditary families that there are often, you can prove that there are some natural separations happening, but they're very far from being non-crossing. You can prove a lot of theorems that say there's separation like this and separation like that, but they cross. This, so you can't go from them to 3 decompositions. But in the bounded degree case, there is a workaround for it. So let me show you what it is. So just for clarity, let me tell you what a star cut set is. A star cut set is a cut set in the graph which is contained in the neighborhood of a vertex. Right? If I can take a vertex and some of its neighbors, delete that and disconnect the graph, then this is called a star cut set. And you can think about, right, cut sets and separations are closely related. You can think about the star separation. So that just means you take the left plus the cut set and the right plus the left plus the cut set and the right plus the cut set, like this, and that's a separation. And star cut sets come up often come up in the study of hereditary graph classes. In particular, they come up naturally in even whole-free graphs. So many people proved many theorems about star cut sets and even whole-free graphs. Okay, so now, so that's what I want to focus on. I want to focus on star cut sets. Now, why? So just one more definition, and then we can start proving things. So a CD separator in a graph is the following. It's a subset of size at most, it's a set of vertices of size at most D, such that if I deleted, every component of what's left contains at most C proportion of the vertices. And it's a theorem of Harvey and Wood that if you're trying to prove that the graph has bounded tree-widths, then you can assume there's no CD separator. I'm cheating you a little bit, but not very significantly. So some setup in which you can assume there is no CD separator, right? For some C and D, there's no CD separator. So now how does it help us? So that means if I look at a set which is not very big, a set of size at most D, such as the neighborhood of a vertex in a graph with bounded degree, right? That's a bounded size set. Then if I delete that, there's a big side, right? Not all components are about the same. There's one component that's huge. Like, for example, think of C being 90%, C being 0.9. So then if I delete in a bounded degree graph, if I delete the neighborhood of a vertex or a subset of the neighborhood of a vertex, there's one component of what's left that contains at least 90% of the vertices. Otherwise, I'm done by the theorem of Harvey and Wood. So that's very helpful. That means somehow for every small set, there's a canonical side. And now what I want to do is to go from vertices to what we call canonical star separations, right? So you have a graph, you have some star cut sets in it. Star cut sets are complicated, right? You take a vertex and now you can look at different subsets of its neighbors that gives you different star cut sets. And then you can partition the components of what's left in different ways. That gives you exponentially many separations. So that's bad. That's too complicated. What I want is to say one vertex, one separation. So that's what we're going to do here. We're going to go from a vertex to a canonical star separation. What does that mean? You take a vertex, you look at all its neighbors. That's a bounded size set. You can delete that. Now there's a big side, right? Otherwise, I know that the tree-width is bounded. And then I'll take the neighbors of V that have neighbors in the big side. So the big side is called B of V. The neighbors of V with neighbors on B of V are called C of V. And then everything else is called A of V. And that's my canonical separation. For every vertex, there's a canonical separation consisting of A plus C and B plus C. And now I'm not telling you, A might be empty, right? I'm not claiming that I did anything non-trivial. It's just for every vertex, I can now define a canonical pair like that. And if the vertex happens to be what we call the center of a star cut set, right? If really deleting the neighbors of V disconnects the graph, then this is a non-trivial separation. But you can define this for every vertex. Okay, so this is the canonical star separation that corresponds to V. And if you don't, if you didn't follow this exactly, it doesn't matter. What matters is for every vertex, there's a canonical separation, canonical star cut set that I'm going to look at. And from now on, no other star cut sets exist for me. Okay, so now I can tell you how the proof goes. So there are two main steps. One is, so it, again, I'm in an even whole free graph with max degree delta, and I'm trying to prove that the bounded. So first of all important star separations can be partitioned into boundedly many laminar collection. Laminar collection means collections of non-crossing separations. So Robertson and Seymour say if you have one non-crossing collection, you can get the 3 decomposition. I can't get one non-crossing collection, but I can get, you know, a million non-crossing collections, which turns out is good enough, right? I can get a bounded number of non-crossing collections. And the second theorem is if you don't have any star cut sets at all, then the treewidth is bounded. This is a theorem in quotation marks, and this is a theorem in quotation marks for different reasons. And this is obvious, right? I didn't tell you. I didn't tell you what it means. You don't know what important it is. And this is in quotation marks because what he proved, what Le proved, is this statement for clique width. But then through known work in graphs of bounded degree, we can also show that treewidth is bounded. Okay, so now we have. Okay, so now let's keep going. So now what I want to say is how far is my graph from having no star cut set? I'm going to define a star separation dimension of a graph, and that is how many laminar collections do I need in theorem 1? How many laminar collections do I need in order to partition all important star separations in my graph? And now the proof is going to be by induction on the dimension. So the way it's going to work, it's induction. Every time the treewidth will go up a little bit, but I'm only going to make boundedly many steps because I know the dimension is bounded, and so it's okay if I go up, you know, a little bit at every step. So here's how it works. So you take one laminar collection of separations, and then you use some very simple variant of the theorem of Robertson-Seymour. You know, it's trivial, it's just in the same spirit. So I say it's their theorem to get what we call a central bag. So what's a central bag? It's a subgraph of G. Really, it's one particular bag of the 3 decomposition that Robertson-Seymour gives you. So you have this one central bag which has the following properties. The first property is if you look at the rest of the graph, it's broken into small components, small meaning each of them is you know, at most 10% of the graph, right? And there are no edges between these small pieces. Each of them attaches an essential bag via star cut set, right? You can recognize this business with the edges of the tree in the 3 decomposition correspond to the cut sets in my collection. But the important part is that this, what we call central bag, has star dimension 1 smaller. And then you can prove that the treewidth of the whole graph is bounded as a function of the treewidth of the central bag. So now you do induction, right? In the base, you have no star cut sets at all, and that's the theorem of Le, star dimension 0, and then you build it up, and every time the treewidth only goes up by a little bit. Okay, so that's the outline of the proof. I'm not going to do any more details of that. But now, you know, now you're in business, right? Anytime you can find a bunch of separations that you can partition into boundedly many laminar collections, plus some more very mild assumptions, you can do this. You can turn the handle and prove that the treewidth is bounded. And so now let me show you all kinds of things we can prove by using that. So this was the proof that even whole free graphs have bounded treewidths. So next, remember there was a theorem that if you forbid long clause, like subclause and line graphs of walls, you get bounded treewidths. Same deal, except for even whole free graphs, to prove that they're star cut sets is hard. It's, many people worked hard to prove that. And in fact, you can't prove there's always star cut sets. Sometimes you need something called a double star cut set, which I'm not going to tell you about because it's just a sketch of everything. But somehow the structure results there are hard. In the case of no claw, the structural results are very easy. If I don't have a claw with legs of size 100, and I look at a claw with legs of size, with 2 legs of size 100, and one leg of size 99, and then I have another vertex. I can't get from this other vertex to the end of the leg of length 99 without going through neighbors of the rest of the claw. This would work much better with a whiteboard, but there's one problem with my traveling. I don't have a whiteboard behind me. I'm sorry about that. But anyway, you get something called claw-centered separations very, very easily. Right? So star separations are centered at one vertex. Now I'm going to take a claw plus its neighbors, and that's a star-centered separation. And then you can talk about canonical star-centered separations, and all kinds of nice things happen to you. And you get to this, you can do the same central bag argument. And then you get to the base case. And in the even whole free case, the base case was the case of no star cut sets. Here, the base case turned out to be the case of claw-free graphs. So if only you could prove that if I give you a claw-free graph with no line graph of a big wall, then the and bounded degree, then the tree width is bounded, then you could get the whole long claw theorem. Now, it's not obvious at all, but we know a lot about graphs. Paul Seymour and I have a structure theorem, hundreds of pages of a structure theorem for claw-free graphs. So you think, anything that's true for claw-free graphs, you should be able to prove. And I don't know about anything, but this you can prove. So you can use the structure theorem to show that they have bounded tree widths, and then you're done. Okay, so I think what I'll do now, I'll just tell you some theorems. I'm not going to do any more proofs. I'm just going to tell you what else you can prove using the central bag method. And then if I have time, I'll say one other thing about the hereditary conjecture, and then I'll stop. Okay, so other results using separation dimension. So first of all, we have an algorithm related to that. So this is not exactly the same because it's an algorithm, not a proof, but we can prove that if you have graphs with no long claw and no n-bounded degree, then you can compute max weight independent set in polynomial time. Right? So it's known that the only chance you have to do it in polynomial time is if you exclude a subgraph of a subdivided claw. And this group conjectured that if your graph is bounded degree and you exclude that, you can do it. And so we proved that. If you exclude this and your graph is bounded degree, you can compute max weight independent set in polynomial time. Another algorithmic outcome is, so remember I mentioned that there's a question, can you compute alpha in stability number or max weight stable set in perfect graphs without using combinatorial optimization? So we've been working on it, and we can do it. So this is a lot of assumptions, but it's not as bad as it sounds. No C4, no induced cycle length 4, perfect, and no prism. And again, a prism is 2 triangles and 3 paths and bounded degree. Now, this by itself is not such an impressive result. The methods are very nice. Uses the submodular functions. Uses submodular function minimization. So we're quite pleased with that. And then the thing is, I expect that this will do the C4, just the C4 free perfect graphs of bounded degree, because somehow there's some sort of standard methods to go from here to there. We haven't done it yet, but I hope it will go through just by kind of classical methods in structural graph theory. This was the part where we needed a new idea, and now we have it. And I should say this is joint work with this group, Tara Abrishame, Jamil Debek, and Christina Ushkovich. So then we got an even stronger theorem. So now back to theorems. So the conjecture is exclude a wall and exclude the line graph of a wall. So I'm not going to exclude a wall. I'm going to exclude kind of one row in a wall. Exclude a subdivided caterpillar and the line graph of a subdivided caterpillar. And then again, you can prove that the tree width is bounded. This is with some new people. So again, Tara and Jamil and me and Sefer Hajabi and Sophie Sprockel. So we have had some new forces join us. And the last theorem I want to mention is it solves a conjecture, or I guess a conjecture of Nicolato Artignon, So Nicolas Trottignon asked, actually not Nicolas Trottignon, it's a paper by several people. It was told to me by Nicolas, but the conjecture is made in a paper by, I think, Trottignon, Philip Chuk, and Thomas, maybe, I'm not 100% sure, I'm sorry. But in any case, what they asked is, what if I forbid a theta? So a theta is two vertices with three induced paths between them, and a triangle, and bounded degree. Can you prove no theta, no triangle, and bounded degree? Can you prove that the two is bounded? And it was open for a while. And again, it's known that if you don't bound the degree, then the two is not bounded. But actually, this method gives very easily something much stronger. So what we do is we forbid the theta, but not any theta, a long theta, right? I fix some t, and I'm allowing you to have thetas where the paths are shorter than t. I'm only forbidding thetas with all possible lengths that is t. And this is called the t pyramid. So a theta is two vertices and three paths between them. This is a vertex and a triangle and three paths between them. And the line graph of subdivided wall, right? But of course, if you forbid a triangle, then this and that are immediately forbidden. And as you say, max degree delta, then you can prove that the two is bounded. So we were quite surprised by getting this result. It is kind of much stronger than what people have been asking about for a few years now. But this method's good. Okay, so that's the last theorem about that. And I still have a few minutes, so let me tell you something else. Okay. So there's some connection. There's some connection between, or you can try to find a connection between 3 decompositions and Dirichlet conjecture. And what would be very helpful is right, so remember again, the Dirichlet conjecture says forbid H, then there's a big clique or a big stable set. What would solve all your problems immediately is if you could prove that in graphs where with no H's in induced subgraph, there's a 3 decomposition where every bag is at most 90% of the vertex set. That would immediately give you a Dirichlet and something stronger. The problem is it's false. There are many graphs where that's not true. The only time it's true if you forbid a 3 in its complement. So that's not ideal. But what if I go for something weaker? I will try to prove that every bag is either at most 90% of the vertices, or it belongs to a simpler class, right? So it's going back to that question, what if, like, I'm not trying to bound the triodes, but I'm trying to decompose, to find a tree decomposition with simpler bags. So, okay, so that's a good strategy, because if every bag is small, that's great. If some bag is big, but it's simple, well, because it's simpler, it contains a clique or a stable set where this exponent is bigger than what I expect in my graph. But it's a large portion of the graph, right? So if I have, if I'm trying for the 100th root, but I can find 90% of the vertices and there I can get square root, I've won, right? And in fact, something much weaker is true. I mean, something much weaker is sufficient. So Paul Simmer and I were trying to use this approach, and for a while we had a good theorem with it, but then we were able to prove something much stronger by different methods with Alex Scott and Sophie Sperkel. But let me tell it to you because I want to mention the method. So it was open for a long time. What if you forbid, these are called caps. It's a hole plus a triangle, a hole in the vertex with 2 adjacent neighbors. If you forbid all caps, is it true that either there's a big clique or there's a big stable set? And we could prove it, so Paul Simmer and I could prove it by exactly this method. We would prove that a graph with no caps has a 3 decomposition where every bag is either small or it's big but simple. And we were pleased about that. But then about a year later, with Alex Scott and Sophie Sperkel, we could prove that it's enough to forbid just this cap and that cap, and you already get Dirichlet. So, okay. And let me stop here. Thank you very much.
So let's thank Maria.
Thank you.
And open the floor for questions. there any questions?
Everything was clear.
No questions? So you may ask in the chat or unmute if you want.
So there's something in the chat. Let's see. I'm not aware of the following recent development in the area. Thank you. I'm going to look it up again. See how I can save it. That's one problem with chats, that I don't know how to.
I think this chat is what I see is from the
No,
previous talk. Nothing new, I think.
Well, yeah, it's new for me. Somebody sent me people. Okay, I guess I can look later. Okay,
Oh.
I'm going to thank you, and I'm definitely going to look at it.
Oh, I see. Maybe you got something in the chat we didn't.
Yeah. Prove the truth and then class defined by.
I see somebody showing a related result.
I see. Okay. All right. Thank you for sending this to me. Okay. Let me close this maybe.
Okay. We have 60 people. Anybody else has any question? Okay, so we can thank Maria, and if people want to join and talk a little bit, we can talk after